What we're going to do today is we're going to really begin to derive new trig identities. So the basic setup is that we have some like core base identities which we derived last time. I'll summarize them in a moment. And the name of the game is to use those core identities to prove and derive new ones, and also to simplify trigonometric expressions. So let's begin by reviewing the identities which you hopefully discovered and sort of derived on your own with the worksheet yesterday. But if you didn't, here's what they are. So we sort of have three groups. So first of all, there are the reciprocal identities. And that's basically saying that every trig function is the reciprocal of another trig function. So, for example, cosecant theta is 1 over sine theta. Secant theta is 1 over cosine theta. Cotangent theta is equal to cosine over sine. And then what else do we have? We have sine is the reciprocal of cosecant. We have cosine is the reciprocal of secant. I wrote cotangent as cosine over sine. That's true, but it's not the identity I meant to write. I meant to simply say that it's the reciprocal of tangent. That's the reciprocal identity. And then similarly here, tan theta is the reciprocal of cotangent. So these are the reciprocal identities. Every trig function is the reciprocal of some other trig function, so these are important. Then we had a couple of sine cosine identities, I think I called them. Basically, this is for expressing tangent and cotangent in terms of sine and cosine. The tangent of theta is equal to sine over cosine. That's really important. I mean, basically, you can think of it as tangent is y over x. Sine is y, cosine is x. And similarly, cotangent is cosine over sine. You can think of it again as cotangent is x over y. Well, x is cosine and y is sine. Then we had a bunch of co-function identities. I'm not actually going to write all these down. They're a little bit less important. They don't show up quite as much. But we have, for example, the cosine of 90 minus theta is equal to sine of theta. If you were to write that in radians, by the way, that would be cosine of pi over 2 minus theta is equal to sine theta, because 90 degrees is pi over 2. And basically every function is associated with its co-function in this way. So for example, cotangent of 90 minus theta is equal to just tangent of theta, right? And you can go on, like cosecant of 90 minus theta is equal to secant of theta. So these identities, it's good for you to see them, but they won't be used that much in our lesson today, and going forward, they don't come up too often. Then we have the Pythagorean identities. The Pythagorean identities are extremely important. Okay, so the basic one was sine squared theta plus cosine squared theta is equal to 1. Remember what this means, this notation with the 2 sitting here. It means sine of theta quantity squared, right? It doesn't mean, right, just remember what this means. Sine squared theta means sine of theta quantity squared. That's what that means, okay? So don't forget about that. So this is our first Pythagorean identity. The other 2 Pythagorean identities are obtained by, if you remember, if you divide all 3 of these terms by sine squared, then you get 1 plus cotangent squared theta is equal to cosecant squared theta. That's our second Pythagorean identity. And the third Pythagorean identity can be obtained from this one by dividing everything by cosine squared. So you get tan squared theta plus 1 is equal to secant squared theta. So these 3 here are the Pythagorean identities. I recommend, you won't really forget this first one. You'll sort of just have it memorized after you use it a bunch of times. The other 2, it's good to have them written down when you're doing these, but if, as far as trying to memorize them, you should remember how they're derived. Okay, you should remember how do you actually get them. Right, remember, you get each one just by dividing either by sine squared or cosine squared in the first identity. You divide everything here by sine squared, you get this guy. Divide everything here by cosine squared, and you get this guy. Okay, then there are also some negative identities. These are a little bit less important, and we've sort of seen them before. Things like, for example, sine of negative theta is equal to negative sine theta. Cosine of negative theta is actually equal to cosine theta. These two terms are the same. And there are similar things for all of them. So the most important ones for the purposes of deriving new trig identities are really the reciprocal and the sine cosine ones, like the ones that express tangent and cotangent in terms of sine and cosine, and these Pythagorean identities. These are the most important ones. Now, as far as deriving new trig identities, we're basically going to use these identities here to crank out more and more and more new identities, more and more new relationships between the trig functions. And, proving or deriving trig identities is kind of a game, and basically there are a few moves that that you can use in order to accomplish the game. So here are the moves, the basic moves that you can use, while trying to prove trig identities. So one of them is what you might call, yeah, sure.
For this one, are we holding y constant as well?
I mean, it's a partial derivative, so like.
Okay, I see. Got it. Okay.
So one thing that we can do is we can FOIL. In other words, we can multiply things out. So if you see an expression like, sine x plus cosine x times tan x plus cotangent x, if you see something like this, you can say to yourself, oh, I should probably multiply all of these things out and collect like terms. So that's one of the moves that you can use. Another move that you can use is factoring, which is basically the reverse of foiling. So if you see something like, for example, sine squared x plus 2 sine x cosine x, you might notice that there's a common factor of sine x here, which can be factored out. So that would be sine x quantity sine x plus 2 cosine x. That's an example of factoring. Another move that you'll see a lot is combining fractions, which basically is like adding rational expressions. So maybe you have something like sine x over cosine x plus 2 over sine x. Maybe you want to combine those two fractions together. To do it, you'd have to get common denominators, which means you'd have to multiply top and bottom here by this denominator, sine x, and then multiply top and bottom here by that denominator, cosine x, and then add those two fractions together. That's another move that you'll see pretty often. Another one that you see often is splitting fractions, which is actually the reverse of combining fractions. If you see something like sine x plus cosine x over, say, sine x, you can split this fraction into two terms by sort of distributing the denominator. That's sine x over sine x plus cosine x over sine x. And then you could say, oh, that's 1, and that's cotangent, and you can say something like that. So these four moves are kind of, some of the most important. So multiplying things out, in other words, foiling, factoring, combining fractions, splitting fractions. And so those are the four moves that you'll kind of use the most often when trying to prove trig identities or simplify trigonometric expressions. There is one sort of move that I want to tell you about, and it's converting everything to sine and cosine. This is kind of a last resort it's something that you do if you don't see anything else that you can do, but it gets used quite a lot, so I don't want to portray it as a total last resort. Like you shouldn't be too hesitant to use it, because it is often quite useful. Basically what I'm talking about is that there will be like a bunch of trig functions floating around, and you convert every single one of them to sine and cosine. Like, for example, if you have tangent x plus cotangent x, and you're like trying to simplify that, and I don't even know that this can be simplified, but if you didn't know what else to do, you could say, oh, well, tangent x is sine x over cosine x, and then cotangent, that's cosine x over sine x. That's what I'm talking about when I say converting everything to sines and cosines. Every trig function can be sort of converted to sine and cosine if you need to. So that's what I'm talking about. So let's have a look at a few examples. So because all of that's kind of abstract, and it's hard to tell really what I mean until you see it. So let's start with some simplification problems. So these are not proving trig identities, but rather just simplifying trig expressions, although the two problem types are pretty similar. Suppose I wanted to simplify the expression 1 minus sine x times 1 plus sine x. Okay? Looking at this expression, hopefully thinking about the different moves that are available to us, factoring, foiling, splitting fractions, combining fractions, probably you notice that you can FOIL this, right? You can multiply everything out. So 1 times 1 is 1. 1 times sine x is sine x. And then negative sine x times 1 is minus sine x. And finally, negative sine x times positive sine x is negative sine squared x. Okay, so that's FOILing out. I multiplied everything out. But then I notice that these two terms cancel, and I have 1 minus sine squared x. Now, that's definitely an improvement over this expression here, but I claim that you can actually go further. If you remember the basic Pythagorean identity, what did it say? It said sine squared x plus cosine squared x equals 1. That's the Pythagorean identity, right? If you subtract sine squared x from both sides from that Pythagorean identity, it tells you that cosine squared x is 1 minus sine squared x. So this expression that we have here is in fact equal to cosine squared x, which is about as simple as it's going to get. So that's that expression simplified. You can see that we so what did we do here? I mean, we used algebra, right, to multiply this out, but then we used one of the Pythagorean identities that we'd already established to go one step further. Let's consider another example. Suppose we have 1 minus cosine squared x over cotangent squared x. So I'm not really too sure what to do here. Maybe I could change this 1 into a fraction and then try and combine the fractions, but I don't really know if that's a great way to go. I'm going to try converting everything to sines and cosines and see what happens. So this is 1 minus cosine squared x over, what is cotangent? Cotangent is cosine over sine, so cotangent squared is cosine squared over sine squared x, right? Okay, so now what you notice is that I have 1 minus this complex fraction, right? It's cosine squared divided by this fraction here. So that's going to be cosine squared x times the reciprocal of this fraction. That's sine squared x over cosine squared x. Now what you'll notice is that this cancels with this, and we're left with 1 minus sine squared x, which if you remember a moment ago, we saw in the last problem that 1 minus sine squared is in fact cosine squared x. So this expression also simplified to cosine squared x, somewhat surprisingly. Okay, so that's some examples of simplifying trigonometric expressions. Let's try to do some problems where we actually prove new identities. So let's prove the following trigonometric identity. How about sine squared x plus 1 over cosine squared x is equal to tangent squared x plus secant squared x. So we have to transform one side of the equation into the other. You could do it in both directions. You could take this side and try to turn it into this side, or you could take this side and try to turn it into that side. I'm going to try to work with this side. Generally speaking, it's better to start with the side that looks more complicated. I would say that this side looks worse. So I'm just going to copy the left-hand side without making any changes, and then, do some work on it, simplify it, use identities, and hopefully I wind up here. So let's see what I can do. First of all, what I notice is that this expression here is just one term, but I ultimately want to turn it into two separate terms. That's kind of a good clue that maybe I should split this fraction. In other words, distribute the cosine squared. So I have sine squared over cosine squared plus 1 over cosine squared x. This sine over cosine, you might recognize that that's actually tangent. So sine squared over cosine squared is in fact tangent squared x. Plus 1 over cosine, you might remember, that's the reciprocal. 1 over cosine is in fact secant, so therefore 1 over cosine squared is secant squared. Oh, but look, that's exactly the right-hand side. So as you can see, I've successfully transformed the left-hand side into the right-hand side. So that's that problem. Let's do another one. How about, well, let's do another simplify problem. Okay, so let's try and simplify something like this, maybe sine squared x minus cosine squared x over sine x plus x. I don't really see a lot that you can do. Splitting the fraction is not really possible. I mean, I guess we could, but I don't really see what good that would do. One thing that I do notice is that the numerator here is a difference of two squares. It's of the form a squared minus b squared. You might remember that a squared minus b squared is a plus b times a minus b. Remember that difference of two squares stuff? So I can rewrite this as sine x plus cosine x times sine x minus cosine x all over sine x plus cosine x. But then what you might notice is that this factor here is identical with this one, and so they cancel. And you're just left with this term here, the sine x minus the cosine x, and that is as simple as it's going to get for sure. Okay, so I think that that's good enough for now.